John, I think you can start with your presentation, then post that. If they have any questions, they can post it out in the chat box.
All right.
So what I'll do is I'll switch off the video so that they can hear you much better.
Yeah. Okay. So you should be able to see my screen there.
So we have biology semester 3, okay, as well as we have a lot of geologists amongst us. Pavitra, yes. Hi, John. How are you doing?
Hi. How are you?
Good. We do have a lot of geologists amongst us, so they'd be very excited to hear what you have to say.
Okay. All right. So look, I will cover a lot of geology, but it'll also be a review of what Mars Society Australia that I'm involved in and Annalie is involved in, the areas we've been working in, including some very recent work in the field of Mars analog research. So are people happy to hear me talk about that?
Yes. Yes.
Yep.
Yes.
Okay. So as you can see, my talk is Mars Society Australia from Arkaroola to the Arctic via Utah and Ladakh. And that pretty well covers sort of the range of our experience and activities. So first of all, who are we? Well, Mars Society Australia is a incorporated non-profit company with approved research organisation status. That means from a taxation point of view, we are equivalent to government research organisations like the CSIRO. So if people donate money to us or spend money on our projects, they can claim that on tax. And our broad vision, what we want to do is to reach out to the public and instill in them a vision of pioneering Mars, particularly for people in Australia, but also worldwide, which includes people in India, people in many other countries as well. We want to encourage governments to spend more on Mars exploration programs. And this includes space exploration generally. When we started as an organization, if we said, well, Australia should spend money on Martian exploration or space exploration, people would laugh at us. That has changed. It's taken 20 years, but that has changed. And now it is something where people are seriously talking about Australia playing a role in space exploration and Mars exploration. On top of that, we do our own Mars research, and I'll be covering that. And we generally encourage Australian participation in planetary science and engineering, in related engineering, industry, and government. So there's a mentoring role for students looking at what they should do in the future. Our membership is open to everyone who's interested in Mars, especially those who want to do a personal contribution. There's lots of societies out there that you can join, that you get a nice magazine, you've got a glossy website where you can learn about all the fantastic stuff we're doing in space. But in MSA, you've got a chance to actually do it yourself. So hands-on work. And we're open to students, teachers, and communicators, to scientists, engineers, tradespeople, technicians, and also people just interested in space or enthusiastic about space and members of the public. So we take everyone from grandmothers through the shopkeepers to scientists and engineers. So what is this analog research that we're being involved in? Well, there's 4 types of Mars analog activity. We look at field science, at operations, which is how you go about doing things, human factors, which is how the human body reacts and the human mind react in a space or simulated space environment, and also in education and training. And we do aspects of all of these. These are some of the programs that we have been involved in. These are field programs starting in 2001 with our first expedition in Central Australia, We've done work all over Australia. We've been to Ladakh, and Devon Island and Utah, and also in programs in New Zealand, Namibia, and the US as well, where we haven't played a leadership role, but some of our members have been involved. And I think this should be an encouragement for you in Amity that you too, starting small, but persisting and maintaining the passion, you could end up doing great things. One of the things we've done too is been involved in suit research. So this is an area that one of our directors, Dr. James Waldy, has been researching for 20 years. If you look at our current spacesuits that we work in on the ISS, that we used on the moon in the Apollo program, that we'll be using on the moon again in a few years when people go back there, we discover they're just not suitable for Mars. They're too heavy, they're too uncomfortable, in fact, they're too dangerous, and they just are not suitable for people going out every other day, every 3 days, and doing work on the Martian surface. And we've been working on designing suits that will solve those problems. And these suits are ones that are what we call mechanical counterpressure suits. They use mechanical counterpressure to supply compression to the body. This means rather than using a gas pressure suit like current suits, we use elastic fibers, pardon me, to pressurize the body. And obviously you need a breathing supply for the person as well. Excuse me. I'll just go to get a glass of water. I'm sorry about that. I'm just recovering from a cold and my voice is quite croaky. My throat is quite dry. All right. So what sort of work have we done in this area? Well, one of the things we did back in 2012 is he took this prototype suit from the University of North Dakota to the Pilbara region in Western Australia and used it to test how well people could do field science while wearing not a simulated suit, but an actual prototype Mars suit. And so this suit, you could actually, it is actually a prototype spacesuit. You could wear it in a vacuum chamber. In 2014 and 2016, we followed up on that work by trials using simulated suits, not actual spacesuits, but simulated ones, seeing how well people could were able to carry out scientific observations, looking in this case for stromatolites. So this area where these people are making observations, there are rocks that contain stromatolites, and we were seeing how effective people were wearing the suits compared to not wearing the suits at recognizing rocks and stromatolites with them. And we also compared the ability of engineers versus geologists, or non-geologists versus geologists, in making those sorts of observations. And what we found, and again, this is published work, is that, first of all, yes, people are able to make valid observations using suits. Rather surprisingly, being in a suit actually seemed to focus people's attention and actually often made better observations while wearing a suit than not wearing one. And we were also able to show there was significant difference in the performance of scientists, of geologists, making the observations, non-geologists. But nonetheless, the non-geologists were still able to recognize the stromatolites there. And this has implications for training of astronauts, that it's really important to have good field geological training in preparing them to look for signs of life, for example, on Mars. Second area of work, for example, we've been involved in has been in field robotics. So this is little miniature lander that one of our people here, Dr. Steve Hobbs, built. It runs off solar panels. It contains a variety of cameras, and the lander itself has a spectrometer on it and a camera on it, and he was able to drive that rover off the lander, all under with solar power, and carry out observations of the Mars yard, which was in his backyard here in Canberra, in a suburb of Canberra, looking at the different rocks over there. Also done a lot of field trials of his robots in, for example, in New Zealand in 2013. He took his robot along to the hot springs, looked at the spectral signature of the biological films in those hot springs. I rather like that top left-hand photo where you can see that the human is making sure it's actually safe for the robot to go. People often say, oh, we can send robots in places where it's dangerous to send people. Well, in this case, we use people to find out whether or not it's actually safe for the robot. This led to 2014 to an expedition we called the Arkaroola Mars Robot Challenge. Arkaroola is a tourist resort in the Australian desert, in the mountains, in the Northern Flinders Ranges. And we had an international team, including a team from Mumbai, from IITB, with a variety of robots they developed. And we assessed their performance using a scheme developed in the US to assess the performance of emergency service robots designed to rescue people from collapsed buildings in earthquake zones. And here's our team of people, grouped the students from IITB, several other universities, MSA people, and so on. And so we had standardized tracks, this sort of torturous terrain they had to be able to navigate. We also made sure that they, how well they went at pulling weights, how far they could travel before they ran out of battery, and so on. So that, again, that's all written up, and I can send you the references if you like. Now, Steve Hobbs has moved on from the field trial of robots, so they're still interested in that, to actually testing in the upper atmosphere of the Earth, in the stratosphere, of sensors and robotic and control systems. So this is a flight over South Australia at an altitude of 32 kilometers. You can see the curve of the Earth there quite beautifully. And this is actually our first flight in 2018, and we're still doing these. And we use weather balloons. We use someone who has experience, has flown over 40 scientific payloads to the stratosphere. And the reason we use these balloons is 30 kilometers over our heads. It doesn't matter whether you're in Australia or in India or anywhere else in the world. 28, 30 odd kilometers over our heads, the conditions are very, very similar in terms of temperature and pressure and radiation to what we find on Mars. So if our robots, control systems, if our sensors will work at those sort of altitudes, they'll work on Mars. At the end of the mission, we terminate the flight. Those balloons have a little self-destruct mechanism, and the payload, which only weighs a couple of kilos, is parachuted back to Earth. And here's some pictures from that. This is views of Western New South Wales from about 20 kilometers or 30 kilometers. Top left image there is a false color measuring the greenness of the vegetation, a system called NDVI. Pardon me. So this is one of the highlights of our program, is when we went to Ladakh in 2016. And this is what helped kick off the Amity program and a Center of Excellence in Astrobiology. So we had a group there of a variety of Indian researchers. We had people from NASA, people from the European Space Agency. There's myself there, Annalie is there, Jen Blank is there as well. And we spent 2.5 weeks at Hunda, at Leh, and at Sokar, assessing their significance as Mars analog sites and assessing the kinds of work that we could do there. I had an honours student with me, Savannah, and she was looking at the sand dunes at Hunda and also the swale sediments. So we've written this stuff up now as part of her honours thesis and also as a paper. She later went on and did a PhD looking at remote sensing using UAVs at the University of Sydney. And so the sort of work that we, for students involved with MSA, the sort of work they do, you can do with MSA does lead on to research and professional opportunities. These are just some more pictures of not that 2016 expedition, but the 2021 expedition, working at Sokar. I was not on that, so I've just used these pictures that circulated at the time, showing the ongoing work in Ladakh, which is a fantastic analog for early Mars. Early Mars would have been a similar environment to Ladakh, low pressure, but much higher than we have on Mars at present, cold with permafrost, we know the hot springs present, and so on. Another area of work that MSA has been active in is in analog stations. At the time of writing, our experience at 2 analog stations, FMARS in the Canadian Arctic and MDRS in Utah, amounts to 872 days by 40 people living under simulated Mars mission conditions. So the vast majority of Australian experience in this area has been with us. We have more than 8 times as much experience as all other Australians put together in this sort of work. So the 2 stations, I know that a lot of people from India have been to these stations now. MDRS is in Utah on the left, where the red star is, and Mars, which is much more difficult to get to, is up in the Canadian Arctic, where the red star is on the right-hand side. So when you go to Utah, what do you see? Well, it is an amazing western landscape. It's like a movie. It's flat-lying Jurassic and Cretaceous sediments, about 150 to 200 million years old, mostly sandstones and shales with minor amounts of gypsum. The mineralogy is definitely analogous to what we see on Mars. We see gypsum, we have a variety of clays, and the kinds of depositional environments of rivers and lakes, and the kind of erosional environments where things have been eroded by wind and gully processes is again analogous to what we see on Mars. The climate is a hot desert, hot summer, cold winter. Astrobiology-wise, there are lots of hypoliths. You break open a piece of sandstone and you find green algae, cyanobacteria living within the rock. Hypoliths underneath the rock, same sort of thing. You turn a rock over and you find green cyanobacteria living there. And halophiles, bacteria, microbes that tolerate saline conditions. From a human factors point of view, isolation is quite limited. It's just outside of town. You can sort of keep people away, but it's not really an isolated environment. So the sort of work we do there is not focused on the impact of isolation on human performance. When I first went there, we first went there in 2003, there was just the central facility there. Since then, it's expanded with a science dome with laboratory spaces. There's 2 observatories there. There's a garage and workshop, and it's largely reliant now on solar power. Devon Island, the Canadian Arctic, is a very different environment. Again, it's made up of flat-lying sediments, old sediments, the Ordovician to Devonian, and they're carbonate rocks with lots of gypsum in them, both as veins and as actual layered sedimentary deposits. Now, this is not Mars analog at all, right? There's very few carbonate rocks on Mars. There's a lot of evaporites, though. But the main analog feature of the geology here is the fact it's in the middle of an impact crater, or on the side of an impact crater. So the station, which you can see there from the air, is on the rim of the Horton impact crater, 22 kilometers across. And much of the crater is filled in by impact breccias, which look a bit like concrete. They're with different types of rocks embedded in a matrix. There's melt rocks and also lake sediments. So one stage, the crater was filled by a lake, these sediments are now being eroded and are well exposed. The climate is cold. It's a polar desert environment, not too different to Ladakh in terms of Ladakh winter, in terms of temperatures. Cold summers and very cold winters. The temperatures in winter get down to minus 40, minus 50 degrees. And as in Ladakh, wherever you go, there's permafrost, about half a meter or so below the surface. And so there are what we call periglacial landscapes formed in environments with frozen ground. And you can see some of the polygons in that aerial shot in the foreground. Again, there are hyperliths, there are endoliths, there are biofilms. There's astrobiological work you can do there. And from a human point of view, this is an isolated environment. It takes 90 minutes to fly there from the nearest human habitation. Devon Island is the largest uninhabited island in the world. It's 90 minutes from nearest habitation. And when you're there, you're there. If you have to actually leave in an emergency, it might take several days before people can be evacuated. It's a very hostile environment. Not only can the weather change at a moment's notice, and you can have blizzards, but also there's hostile life forms there in the shape of polar bears, so that when you go outside, you always have to have someone who's on guard duty, not in a simulated spacesuit, but carrying a shotgun in case you're attacked by polar bears. So here's some of the expeditions we've done there. Back in 2016, I was involved in a project called Mars 160, and that's meant spending 80 days at the Mars Desert Research Station in Utah, and then the following year, initially, we're going to spend 80 days at FMARS. So this is photos from the first half of our expedition in Utah. We tested out equipment. We carried out geological observations, and we also did things like plant growth experiments. And Anushri Srivastava, who's now working on the Perseverance rover science team, was looking at hyperliths and halophiles. She later went on and did a PhD at Open University in the UK, and now, of course, is in the US. We had people from France, from Russia, from the US, Canada, as well as Australia. So it was a great international team working together. Another group, this was last year. We had a crew 291 working in Utah, mostly doing robotic studies and human impact studies. So these are all from Australia or MSA people. Crew 292, immediately following them, was led by Annalee Beattie and had mostly people from India who were studying in the US and UK. They did a wide-ranging series of investigations there, only for 2 weeks, just like Crew 291 on the rocks. They did a lot of biological work and a lot of mapping studies as well. Now, in terms of going to the Arctic to FMARS, the second half of the Mars 160 expedition took the same crew and put them in the Arctic, where they were able to do our geological research and our astrobiological research there. In the top left picture there, you can see someone out of a simulated spacesuit carrying a shotgun, and their job was to keep a lookout for the bears, while in that case, Anushri was doing her field work. And we were able to do a wide range of field studies in these simulated spacesuits. And yeah, life in the Unican, life in these simulated HABs. I mean, life went on. If you went outside, with one or two exceptions, we always put on the suits. One of the exceptions in the top right there, where people went out and incinerated all our rubbish, including all of our biological waste. We cooked together. We lived together in this environment for over a month. Last year in 2023, we also sent an Australian-led team to FMars, and here they are, 5 people working, doing geological work and a lot of repair work on the station, which has been up there for over 20 years. And they did sewing on the spacesuits, they repaired the insides, and they're able to do some geological work as well. And I'll finish up by looking at some of the education and training work that we've done focusing on the Central Australian Analog Expedition in July, August last year. So on this trip, we looked at impact craters, we looked at lava caves, and we also looked at salt lakes. So in this slide at the top here, we've got the Henbury crater, which is it's only 180 meters across. It's about 4,000 years old, formed by the impact of an iron meteorite near Alice Springs. And it actually broke up at low altitude. It's a cluster of about a dozen small craters. We went to Goss's Bluff. Those hills in the center are actually a ring of rock around the central part of an impact crater that's about 30 kilometers across. It's deeply eroded, so you don't see the outer rim, and you just have this central ring of rock 5 kilometers in diameter. Here are the lava caves. On the left, top left, you have the entrance. You get in through the skylights. In the bottom left, you can see the route down through the skylight, climbing over those rocks, some which are the size of cars. And when you get inside them, what was surprising to me was that I'd expect just to see bare rock. But in fact, the rocks are covered by these knobbly growths formed by bacteria. When you put an ultraviolet light onto the rocks, you can see all of these microbial colonies fluorescing in different colors of blue and turquoise and green. And when you touch the surface, in most places, it's not hard rock. It's actually soft, composed of microbial mass. So that's a big surprise to me. Jen Blank, who I believe you'll hear from later, was on that trip, and she's done a lot of work in lava caves. I'm sure she'll talk about these in more detail. And I've just come back. I haven't got the photos here, but we've just come back from repeating that trip with a different group of people, again, very successfully. So in closing, I'd like to summarize, what's been the impact of what Mars Society Australia has done? Well, starting with Jantamara, back in 2001, we selected Arkaroola as a prime site for our work in South Australia. It also led to NASA-funded research at Dalhousie and Mount Springs. The Mars skin work that we did to simulate spacesuits led us to get a contract to supply such suits to the Victorian Space Science Education Centre, about 40 suits in all, which they could put students into to do education. Our expeditions have all led to papers, multiple papers, and in some cases monographs, books. Our Space Abound program has led to education and outreach across 5 countries, particularly the Ladakh expedition, which was the most recent one we did, and led to the center of the Amity Center. Arkaroola Mars Robot Challenge was an incentive for Australian Indian institutions to send students to other robotic and ongoing robotic expeditions and competitions in the US and in Europe, and to start setting up their own here in Australia. We're able to collaborate with NASA, with ESA, Institute of Biomedical Problems in Moscow, Amity, BSIP, various Australian and US universities. We're able to prepare policy documents informing Australian research community and policy people, such as the Australian AAS, Australian Astronautical Society, and also the CSIRO in their preparation of reports for the government. And we've done a lot of publications, 4 PhDs, 3 honours theses, at least 2 books, and more than 70 peer-reviewed publications. Not bad for a volunteer organisation. So you can find out more about what we do at our website or by contacting us. So I think that's enough from me about what we do. Are there any questions?
Yes. John, thank you for that talk. I hope you can hear us.
Yes, I can hear you.
Thank you. John, are you there?
Yeah, I'm here. Can you hear me? I can hear you. I can hear you.
So I said thank you for the talk. Yes, yes. So thank you for giving us the analog of all the previous experiences and all the other expeditions. So that was really good. Does anyone have any specific questions about that? Okay. So we do have a couple of questions, so you can just come up front and then ask a question.
The screen's gone blank
Hello,
from
Dr.
your
John.
end.
Yes, one second. Yes. Hello, Dr. John. This is Aditi from MSc Astrobiology and Spacetime. So I have this question. I have recently read that since there are deposits in Australia are analogous to the Puga hot springs in Ladakh, and I had the question that how do the geochemical characteristics and mineral deposits of Puga in Ladakh, how can we compare them to those we find in Pilbara, and what implications would they have in context of origin of life? Like,
I got some of that. I'm just wondering, would it be best to type your questions into the chat? The sound is not very good from your end. So if there's a chat box there, and you can send me a text with a question in, and then I can answer. Is that helpful, Renita? Yeah. So I got some of that,
yes,
and I think it's a very good question.
I can try is I can stop the I can stop the video and we can give it a shot if you want to.
Yeah. It's all the sound quality that's the problem. So perhaps you just type those questions. Turn the light on.
Okay. We're just typing the question, John.
Yep. Looks like quite a complicated, long question.
Yes, yes, that's exactly what we were saying.
Okay. Pilbara deposits are analogous to Puga in Ladakh. Yeah, that's an excellent question. So, a couple of years ago, people studying the ancient hot spring deposits in the Pilbara, which are about 3.5 billion years old. Some of the oldest signs of life on Earth. There you get biofilms, fossilized biofilms, stromatolites, some which are quite small, about centimeter size, some which are somewhat bigger, like an egg carton. And the very oldest ones, to people's surprise, were not formed in marine environments, but on land, in pools of water. Hot springs on land are quite small, around old volcanic centers. And not only do they contain signs of life.
John, we couldn't hear you.
You can't hear me?
John, are you there?
Yeah, I'm here. Can you hear me now? Right. No luck. Okay, how about I type my answer?
Hello, John?
Hello, I can hear you.
Yes, yes. We couldn't hear you. Can you
Okay,
please repeat it?
yes, can you hear me now?
Yes, yes.
Okay, good. So, a great question. Several years ago, people found signs of life in ancient rocks in the Pilbara. These have been known for many years, in fact, but these ones they found were a little bit older than the others, and they were found to be not in marine hot spring systems under the ocean, but they actually formed in little pools, hot spring pools on land 3.5 billion years ago. And they have stromatolites in them, and they are also very rich in the element boron. And this is why we were interested in Puga, because in Puga too, we have hot springs in an on-land environment, and which are very rich in boron. And so we actually had an honor student who was
John, we can't
working.
hear.
You still can't hear me? Can you hear me now? Perhaps you can I don't know, turn your camera back on. I'll type a message.
Hello?
Yes, I'm typing my answer.
Okay. Or you can maybe send a voice chat to the WhatsApp later, maybe.
Yeah. Okay. So I've just sent an answer to that question about Puga. But we could use WhatsApp if that's easier.
Okay. So we have a second question also.
Yes.
How much positive we are after getting an analysis of data from the Mars rover mission about existence on life on Mars.
So you want to know whether how much the Mars rovers have helped us understand life on Mars? Is that correct?
Yes.
Okay. The Mars rovers have not found life on Mars, but what they have told us is the kind of environment that life, if it ever existed on Mars, what kind of environments they might have lived in there. So we know at Jezero crater, where the Perseverance rover is, that we're looking at a delta feeding out into a lake. We know that there was a carbonate spring deposits around the margin of that lake. We know that there are hot springs at Gusev crater with lifelike stromatolite-like features in it. We can't say that there actually are stromatolites, but there are signs of stromatolites, of lifelike processes going on there. The Perseverance rover has found different times of lake bed deposits on in Gale crater. So all of the rovers have given us a picture of what the ancient Mars environment was like, and it appears quite hospitable. Whether there was anything living there, we are yet to find out. That's why we need to bring samples back from Mars so we can do the kinds of very sophisticated analyses necessary to prove that life was there or not.
Okay, thank you, John. Anyone, any more questions?
No?
Yes, any more questions? Okay. I think we don't have any questions.
Thank you for your patience putting up with this crazy Australian geologist. I hope I did not talk too fast. I hope it made sense what we're talking about. But I'd really encourage you in first of all, in your interest in planetary science and astrobiology. It doesn't really matter whether you are interested in the engineering side or the science side, and what kind of science you're in, is you can bring that knowledge to these questions of how do we understand the search for life in the universe. So thank you for being part of this course, and thank you for listening. Okay.
Thank you so much, John, for connecting with us today. And I'll share your email ID to all of them in case they have any further questions or they would like to connect to Mars Society Australia, so they can connect to you.
Yeah, I'll be very happy to answer any further questions that you have. So just email them to me or send them on WhatsApp, and I'm happy to answer them.
Yes. So,
yeah.
Thank
Catch you later.
Bye.
No worries. Bye.
Okay, Mobin. हेलो
यस मैम यस मैम
हम अभी का सेशन तो हो गया है, तो आप इसको क्लोज कर सकते हैं। अभी शाम को 5 बजे है हमारा, उसमें भी आप ही हो क्या?
हाँ हाँ 5
ठीक है, तो हम लोग 4:45 तक कनेक्ट कर लेंगे। ओके
ओके मैम